Aloha. So in this problem, we're talking about a ship that's carrying fresh water to a deserted Caribbean island. And we're told that the area here at the waterline, which we'll call A, is 2,240 meters squared. And after it drops off the water at this island, it rises in the water line by 8.2 meters. So I'll call it distance h, this height that it changes by. And we want to find the volume of the fresh water, which I'll label VFW. So we can analyze this problem thinking about the forces on this boat. There'll be a buoyant force keeping it from sinking and opposing the force of gravity. And there's two cases, and I'll call this one the first case when it's carrying the fresh water, and then there's another case when it's dropped off the fresh water. It's a bit lighter. And we can write down the buoyant force always using Archimedes' principle. So in general, that's the mass of the water displaced times g. So it'll be the density, and here the water is really, we're talking about salt water, which I'll label SW, times the volume, which I'll label V1 in the first case. And basically we can just, consider the first situation. It's carrying both the fresh water as well as, so we have for the mass, M1 will be the mass of the boat. I'll just call it MB plus the mass of the fresh water. And since these forces are balanced, it's not moving up and down in the water line, we can equate for the first situation these two forces. So that means just combining this with our expanded way of writing out this total mass here and the buoyant force from Archimedes' principle, we know that we have density of the salt water times V1 times G is equal to mass of the boat plus mass of the fresh water times G. So you can get rid of the factor of G there, the acceleration due to gravity. And note that we can write the mass of the fresh water as a density of the fresh water times a volume of the fresh water. And this is good because that's what we want to find. We want to find the volume of the fresh water. So I'll rewrite this equation out again. And then we can rearrange this. We have this as equation for the volume of the fresh water. This is what we want to find. And then we can consider the second case when the fresh water is dropped off. So we know that there's a balance of forces again. And M2G is just the mass of the boat times G, because there's no more fresh water on board. We're assuming that's the only cargo here. And the buoyant force will be the density of salt water, that's the times the second volume. It's risen a bit, so the volume displaced is a little less. I'm calling that V2 times G. So again, you can cancel out the acceleration due to gravity. So that leaves us with an equation for the mass of the boat, which we can plug in to this equation up here. So I will rewrite this equation again. For the freshwater volume, which is what we're looking for. and using what we found from analyzing the situation with the water already dropped off. So I'll factor out the salt water density over the density of the fresh water. And these densities you can find in a table in the textbook. And then we're just going to consider the difference in the volumes displaced. And I think we can just assume here that the area is something constant. So we know that a volume can be a cross-sectional area times some height. And in both cases, we'll assume that the area where the water level is the same. So you can factor out an area A, and then we know the difference between these two was given. That was the height H, the amount that the water level dropped. So this will be our final equation then, because we can look up the densities in the table for saltwater and freshwater. This is an equation in terms of variables we can just plug in and solve for. So the volume of the fresh water will be just plugging in the numbers here. That's the densities, and then the area was, we were told 2,240 meters squared, and the height difference that it dropped was 8.25 meters. So those units will cancel out and you'll get an answer in meters cubed, which is what we want. So there's your answer.